So I'm going to talk about the spread of ideas, the complexity theory of flash mobs. So here are some of the questions that I asked. Basically, I want to know why flash mobs form. Now, my definition of a flash mob is any organization, a group that forms either online or in physical presence, such as Occupy Wall Street or the Arab Spring or other ones that you might be familiar with, and then they dissipate. They come and go. They tend to create an event, and then after a period of time they tend to dissipate, and that's what I'm interested in studying. And then what might you do about them if you choose to, let's say, break them up, or if you choose to control them somehow. So you may not know it, but CHDS alumni form a flash mob. And this turns out to be a video of the last 8 years of interactions at CHDS online. The posts that you made on Moodle have been recorded. We had to go to WikiLeaks to get them. No. And this is simply a movie that plays them back. So each dot is one of you. Each link is a post. So if you post a message during a class or during the alumni network interactions, that post is recorded. And it's been recorded since 2005, all the way through, I guess it's still being recorded. And this is essentially a movie of those 8 years compressed down to roughly 3.5 minutes. So now you should be able to see the formation of clusters taking place. In other words, CHDS interactions are self-organizing. You as a group form subgroups, and some of those groups are more tightly connected than other groups, and so forth. I don't know if you can see it, but in the peripheral are people that are not interacting. Those are, I guess, innocent bystanders, but I prefer to think of them as people that fell asleep in Bellavita's class. Sooner or later, those people will get engaged, they'll post something, and they'll be sucked into that central core that's being formulated, okay? And there also, you'll see, ultimately, there are some outlier clusters that are being formed. And one of them that was rather sizable was connected to the rest of us through a single individual. So we wanted to find that individual and punish them. No. We wanted to find out who that was and why that was being formed the way it was. Turns out that's the citizen area network that was started up by the Coast Guard that kind of branched off the CHDS alumni network and took on a kind of a life of its own. Okay, so the first thing you might observe about this is that there's some kind of clustering or formation taking place automatically. There's no central control. Nobody at CHDS is telling people to post. Nobody is telling them to cluster together into groups or whatever. They're just doing so kind of as a byproduct of interaction online. This is actually my class, the CIP class of 2012. It's a year ago last spring. This is the same idea applied to 25 students in a class. Okay, so the size and coloring of the nodes has to do with their influence over the network. So if a large red node, for example, is the formation of a hub. The small green and blue ones are people that are interacting but at a lower level. So we use this in class to spy on you. No, we don't. We use this just to see the formation of the group, what's happening in the class. So this was over a 3-month period from March 2012 to May, the end of the course in 2012. The big red dots are the 2 instructors, because they interact most often with the other, everyone else. And then off to the left, there's some statistics about who's forming the most binds with other students through posts, and who might be the most influential in terms of propagation of ideas. The NSA knows all about this. No. So the question is then, why do these social networks form? What causes them to form? Can we understand the levers that you might pull to make them form or make them stop forming, etc.? So that was a question I posed for myself. So there's one previous work done by Craig Reynolds, who received an Academy Award for this work. And I bring that up because of the Academy Awards that just took place. And unfortunately, Craig received this 20 years ago. And if you've seen special effects in a movie, where you see flocks of birds flying around or legions of army out in the background, that's all computer generated. And the algorithm behind that is this flocking algorithm that Reynolds invented back in the he received an Academy Award in 1998. And again, the dots are individuals. In this case, they're called boids. This is Craig Reynolds' definition of boids. So boids form flocks, and they fly around at random, but they're not very smart. Okay? They're just applying 2 simple rules. Rule number 1 is stay up with the flock, and rule number 2 is don't bump into nearest neighbors. And that's all they do. And just by observing those rules, it actually causes them to move. And frequently the lead bird, the alpha bird, the leadership changes, and this changes the direction of the bird. So if you see flocks dashing one way and dashing the other way, they're basically changing leaders as they do that. But there's no clear-cut pattern. There's no central control. There's no authority that's telling them, hey, we should do this or do that or the other thing. So the question is why? And the answer is these 2 simple rules. They fly toward the center of the group, and they avoid their neighbors. They don't want to bump into neighbors. Actually, avoiding your neighbors in this kind of thing is what causes the flock to move, to actually move from place A to place B. And then which one you follow is dictated by flying toward the center. So I don't want to suggest that students are birds, okay? But this gives us a clue about the self-organization as groups, either online or in physical space, as things such as Occupy Wall Street or Arab Spring take place. So here's a snapshot. I don't have a movie of this, but this is a snapshot of Facebook. I think this is from Facebook followers online. And notice that the formations are very similar. You'll see the dark clusters areas. There's 3 or 4 of them. There's some that are scattered about, but they form this organization. But nobody on Facebook tells them to do this. There's no central authority on Facebook saying, hey, you ought to send a tweet or a response to certain people. So again, this is a very similar pattern. For those of you who love math, the size of these clusters follows a long-tail distribution. And that'll be a key to understanding extreme formations of these things going forward. So clusters form because of homophily. How many of you did you have a class that discussed homophily? Does everybody know what the definition of homophily is? The simple definition of homophily is birds of a feather flock together. That is, people gravitate or they take on the attitudes of the people that they directly associate with. So if you belong to the Elks Club, it's because you share those values. If you belong to Another club, you share those values. Homophily is a clue as to why these things form. So what about Occupy Wall Street? If you do the math, it turns out that the Occupy Wall Street is an example of a self-organized flock. That is, it's one of these long-tailed distribution in terms of size as defined by online posts. So this is the actual data from the Facebook online posts over a period of time of several months during which the Occupy Wall Street was taking place. Does anybody know why Occupy Wall Street went viral? Social media, but what was the spark? What started it? Okay, so in this case, there was an instigator, the Adbusters magazine, which has a subscription around 70,000 people. The editor of Adbusters magazine called for the march on Wall Street on a certain date, and that was what actually got people together. Now, why did people gather around that cause or that idea? Well, that's a different story. But the fact that they did, they gathered around, they showed up on the streets of Wall Street, and they grouped together for a period of time, and then they dissipated, right? So if you look at the distribution of size of groups online that are tweeting about Occupy Wall Street during that period of time, you get the group size as a long-tail distribution. The only utility of that is it shows that this is an extreme event. If it were not an extreme event, this would be a mountain-shaped normal distribution. It would come and go, and there would be a certain average value, and then values off from that would be symmetrical around the mean. But that didn't happen. Instead, it's a long-tail distribution. So you can ignore the math. The point here is that this was an extreme event. It's also interesting to note that it's what we call punctuated in size and time. So what do we mean by punctuated in time? That means the time elapsed between flash mobs is also long-tailed. Okay, so I haven't done this, but if you look at, say, shootings, active shooters, and you plot them, the number of casualties, the separation in distance, the separation in time, my guess is that they would look like this. They'd be a long-tailed distribution. That is, in time, that means most of them happen close together. A few of them are sort of outliers, happen after relatively long elapsed time. So what's the utility of this? Well, you can sort of gauge what's happening and what might happen in the future by, this is kind of a predictive analytics approach to it, right? So flash mobs distribute in space according to these long tails also, which means most of them happen locally, but some of them happen a long distance away from the kind of the center of the storm, if you will. Okay, if you want to look at this data, this, by the way, is actual data from a website called violentflashmobs.com. You can go there and look at the data for yourself, but you can actually, these data are collected and posted there, and then you can analyze the data. If you did the same thing for Al-Qaeda, the attacks for Al-Qaeda, you'd find the same pattern. That is, you'd find they're distributed long tail in terms of size of casualties, in terms of elapsed time between attacks, and in terms of distance from the previous attack. So it gives you kind of a triangulation mechanism for predicting when, where, and how large the next attack would be. So flash mobs are extreme and they self-organize. They form herds or groups. They're examples of normal accidents. They're connected events. That is, the likelihood of the next one happening is based on if the previous one has happened already. And they're long-tail events. They're black swans. How many people know what a black swan is? Oh, that's a little bit better. Okay. The question is why? So this sets the stage for doing research in complexity theory to try to explain why these things happen. So here's the model. This is Occam's razor. How many people remember what Occam's razor is? So the simplest explanation is the most likely explanation, right? So Occam, everybody got that? Occam's razor says, when in doubt, use the simplest explanation possible. Well, the simplest explanation possible for flash mobs that I could think of was that whether or not you are pro or con a certain position, as evidenced here by coloring this network, this social network, as either red or blue. So red is one position, blue is the other position. And if you don't have a position, then there's no color. So whether or not you decide to take the position of red or blue is proportional to the number of neighbors that you're connected to that are red or blue, right? So here you have a simple math problem. You count the number of red neighbors and divide by the total number of neighbors, and that gives you the likelihood that you also will be, on the next step, you'll also adopt the red position. Everybody get that? So that's pretty simple, right? So what it says is that your attitude about something is more likely to be like your friends' attitudes or your neighbors' attitudes than not. That's homophily. So you might try this experiment with your friends. You get together with 5 or 6 friends and you say, which movie should we go to? And typically the first movie mentioned is the movie that you go to. Why? Because everybody around you, a certain percentage, will adopt that position. Okay, or you go to a CHDS banquet and you ask what you want to eat. Typically the first person to order, well, a larger percentage of dishes served at that table will be that first one mentioned. Okay, again, this is homophily. So we're going to apply this homophily to a computer model. So here's the model, and all the model does is it assumes a social network. These are nodes that are connected, just like we saw on the CHDS flocking example, that are connected somehow. They know each other or whatever. That's wired up that way. And we just repeat the experiment. We count the number of red neighbors, divide by the total number of neighbors, and that's the likelihood that I'll paint myself red. And we just do that over and over again. So your initial reaction to this is, why doesn't everybody end up red at the end? Right? There's one little fix on this. There's 2 nodes that start out that are fixed, one at red and one at blue. Everybody else has no color at all. Then you repeat this experiment over and over again. The computer does this work for you. And what happens? Well, you'd think that they all end up one color or the other, right? But that's not what happens. What actually happens is you get a long-tailed distribution of size. Most of the groupings, most of the size of the red group are small. Occasionally, very rarely, you see this is the long-tailed distribution, very rarely there's a large group. In this case, there are rare ones about half of the group is all red or half of the group is all blue at some point in time. In other words, it dynamically changes, right? Even though you think, hey, this should all turn all one color and stay that way, or not. So what's going on? Well, if you plot the self-organization versus time, as you can see here, reds and blues, you can actually predict a future switch from reds to blue based on the level of self-organization, let's say, of reds. So you see the red, self-organization value of the reds, if they go down, the blues go up, and if the blues go up, the reds go down, they'll switch positions. So you can actually see the sentiment, if you will, switch from red to blue or blue to red over time. And it's sporadic. That is, it follows a long-tailed distribution. So how can you manage something like this? Well, the answer is the most influential member of that social network is the one that has the most connections. That's pretty obvious, right? Pretty simple. So if you post the first one, red, that has the most connections, red will dominate over blue. If the first posting is blue, then blue dominates over red. That is, the member of the social network with the most social connections dominates the group. So we used this in the example simulation of the class that I showed you at the beginning. The student with the most posts also had the most influence over the group as measured by the topics that were discussed. They become the dominant topic discussers in the group. And we had to shut them up. So in this little chart, you see that the long tail distribution goes away for red, and the red hub causes the average size of the red group to peak near 100%. So one way of controlling this, or seeing how control works in a social network, is to find out the most active social member as indicated by their connections to the rest of the group. Another factor that seems to be working is in a dense network, that is a network with lots of connections, they behave different than sparse networks, networks with not very many connections. Okay? And that, contrary to what you might think, a dense network is more normal, i.e. the positions red or blue are typically follow a more normal distribution. But for the sparse networks, they're still extreme. They follow a long-tail distribution. So what this says is that if you're a member of a social group, and let's say you're on Facebook or whatever, and the average number of friends on Facebook is roughly 130. So let's say you have 130 friends on Facebook. Then if you listen to all 130, your behavior, your positions on things will be somewhat normal. Okay, that means it's sort of the average value. Okay? If you only listen to 5 or 6 or a handful of them, then your position will be extreme. That is, you'll be one of these long-tail distributions. So that means that extreme groups are groups that listen to a subset or maybe the loudest voice or the most outspoken members of their group, and not just to everyone. Okay, there's one other factor. If you're stubborn, it matters. So if it takes a strong argument to overturn your position, if your position is red and it takes a lot of persuasion to get you to change your mind to blue, so you're stubborn, then this also affects the self-organization of the network. What happens in this case is that the more stubborn the individuals are in the group, the more normal. The less stubborn, i.e., let's say weak-minded, the more likely the group is to be persuaded and to have these extreme behaviors. Does this say something about the US Congress? Okay. Okay, so what did we learn from this? Flashmob spontaneously organize. The first rule is your sentiment is like your neighbor's sentiment. The majority position is determined by your connections, your degree, unless you're stubborn. And then dense networks are less extreme. So all of these things that we saw examples previously, Boyd's, flash mobs, epidemics, both internet viruses and human epidemics, they all self-organize like flocking birds. They take Levy flights. Remember, Levy flights are long-tail distributions. They forage. They exhibit extreme behavior because of the structure of the network, and that's the key thing. It's the structure of the network that determines the behavior of the people in the network or the actors in the network. So by now you should be saying, well, so what? When is lunch, right? So what? Well, how could you actually use this? One idea is maybe it could be used to control flash mob, to break up civil disobedience or to just control an online flash mob. First of all, you can, by measuring the amount of self-organization taking place, you can predict that a flash mob of certain size will happen, but you don't know whether it would be good or bad. It could, United Way fundraising could be a flash mob. That could be good. Or it might cause trouble. You don't know whether it will cause trouble or how large or how sizable the trouble might be, but you can detect that there's a mounting self-organization that's taking place, it's building up, and that something's going to happen. So this is currently a hot topic in research done by companies like Google, Facebook, and Twitter. They'd like to be able to predict how many Teslas you're going to buy by looking at social groups organizing online, and then, are they persistent? Do they stay around? Do they grow? Do they cause purchase decisions to be made? But for our purposes, maybe what we want to do is just control crowds. So here's the strategy. It's known as the blocking node strategy. And the way it works is also Occam's razor. It's very simple. You simply identify the actors in the social network that if you take them out, it separates the social network into disjoint pieces, into islands. Now, how do you actually find this? That might be kind of difficult, okay? But if you find this, this is a way to dissipate a crowd, an online crowd. So here's the 9/11 hijacker network. There were 62 perpetrators in the 9/11 attack, even though there was only roughly a dozen that participated in the actual hijacking. And as you might guess, Ada was at the center of this. Ada was claimed to be the leader, and that's evident in the social network because Ada is the most highly connected member of that network. There are lieutenants, as you can see. This is organized by connectivity. The more connected members are moved toward the center of the diagram. The less connected ones are out in the peripheral. So you can see Ada's in the center. And then there are lieutenants that are semi toward the center. And then there are members, outlying members. So if you knew this social network, then the question is, what are the minimum number of people that you take out to disrupt the network? What's the smallest number of that cell, if you want to look at it that way, that you can eliminate or make ineffective and disrupt the network? And these are called the blocking nodes. So you can identify the blocking nodes. There are ways to predict how many there are, and then there's computer ways of identifying who they are, okay? And if you do that, then you can take those individuals out, and you can see what happens is it breaks the network up into islands, and the argument is that they're less effective because of the way you took out the appropriate members of that network. You want to take out the minimum number that does that, okay? And in most cases, in most social networks, because there's a few people that are highly connected and not very many people that are not very much connected, the number of people that you need to take out to disrupt the network is typically very small, on the order of 10 to 15%. So you don't have to attack the entire cell. You attack the 10 to 15% that are the so-called blocking nodes. This is also effective for combating infectious diseases like SARS, okay? And it's also effective in disrupting viruses that might spread via the internet. Okay, in the case of the internet, the 1,000 top internet websites requires you to remove about 11% to protect the internet from the spread of virus. So this is a somewhat generalized idea that could be used for a number of things. Blocking nodes are the key actors in marketing products, stopping contagions, stopping power grid collapses, controlling flash mobs, persuading group members to be pro or con, maybe even in diplomacy. Okay, so that's sort of the takeaway. And Heather promised that I could advertise my next book. So this comes from Book of Extremes, the second chapter, which will be out from Springer and late in this year. And that picture of the cover is the Big Sur beach with waves lapping on it, taken from the air. Okay, have a good meeting, everybody.